Hi everyone, welcome back to Coding Fab. In today's lesson, we're diving into one of the most iconic beginner-friendly machine learning projects, Titanic Survival Prediction. You'll learn how to explore and clean the data, engineer meaningful features, build a classification model, and evaluate how well it predicts who survived the Titanic disaster. We'll use Python and libraries like pandas and scikit-learn to guide us through each step of the process. If you're new to machine learning, don't worry. I'll walk you through everything clearly and slowly so you can build confidence while learning the key concepts. You can pause, rewind, or take notes as you go. This is all about learning at your own pace. All right, let's get started. 1. Understanding the project. This is an example of classification with tabular data. This project belongs to the classification category of supervised learning. The main goal is to predict whether a passenger survived or not on the Titanic using features like age, gender, ticket class, and more. The output is binary. The model predicts either survived or not survived. The data for this task comes from the Kaggle Titanic dataset, one of the most popular beginner-friendly datasets in the machine learning community. The dataset is in tabular format, with structured rows and columns representing passenger attributes. We will use logistic regression as the main algorithm. Logistic regression is a simple yet effective method for binary classification problems and serves as a strong baseline. To evaluate the model's effectiveness, we will use classification metrics such as accuracy, the overall correctness of the predictions, precision, the proportion of predicted survivors that were correct, recall, the proportion of actual survivors that were correctly predicted, F1 score, the harmonic mean of precision and recall, especially useful for imbalanced data. We will develop this project using Jupyter Notebook for an interactive step-by-step workflow. The tools involved include pandas for loading and manipulating the data, scikit-learn for building and evaluating the model, matplotlib for visualizing data distributions and model performance. Also follow the basic machine learning workflow shown in the upper right. Okay, let's get started. 2. Data collection. Let's download the dataset into your system. To collect the data, visit Kaggle. Go to the competitions section and search for Titanic Machine Learning from Disaster. Then navigate to the Data tab. You will find 3 CSV files: train CSV, test CSV, and gender submission CSV. For this task, we will only use the train CSV file to build and test our model. So click the download button to get the only train CSV. Once you download the data, you'll see these features in target label. The train CSV file contains information for 891 passengers. Each row represents a passenger, and each column provides a feature or label. Target label is survived, whether the passenger survived or not, 1 or 0. The main features are, for example, P class. It's a ticket class. 1 is first class, 2 is second class, 3 is third class. Others are sex, age, number of siblings or spouses aboard, number of parents or children aboard, port of embarkation, and more. We will prepare and process these features in the following steps to train a model that predicts survival outcomes. 3. Loading the data. Same as the regression task, import the dataset into your Python environment. You'll see rows and columns with meaningful headers like passenger ID, P class, sex, age, fare, and survived. Make sure the CSV file is uploaded into your file browser before running the pandas method. 4. Exploring the data. The goal is to understand the structure of the dataset. For example, by using the shape method, you can understand how many rows and columns there are. In this case, 891 rows and 12 columns. The columns method shows what each column is called. The info method tells you the data types of each column and whether any values are missing. In this case, age, cabin, and embarked have missing values. The describe method shows stats like mean, min, and max for numeric columns like age, fare, and so on. In addition to that, there are many other insights that can be gained from this step. Value distributions like the frequency of values in categorical columns such as sex embarked, P-class, outliers and unusual values, relationships between features and the target like survival rate by gender or class, duplicates or irrelevant columns like identifying columns like passenger ID, name, ticket, which may not help in prediction, potential feature importance like noticing which features seem related to the target by looking at patterns. Data quality is like assessing if the dataset is clean, balanced, and ready for modeling. In the next section, let's visualize some data to understand relationships between features and survival on the Titanic. Okay, let's visualize some data. First, survival by sex. This chart compares survival rates between males and females. Females have a significantly higher survival rate, around 75% compared to males, around 19%. So the gender is a very strong predictor, possibly due to the women and children first evacuation protocol. Next, survival by passenger class. This bar chart shows survival rates across different passenger classes. First-class passengers have the highest survival rate, around 63%, followed by second class around 47%, and third class have the lowest, around 24%. Passenger class strongly influences survival chances, likely due to cabin location, access to lifeboats, and social status. Next, survival by port of embarkation. This plot shows the survival rate by the port where passengers boarded. C is Cherbourg, Q is Queenstown, S is Southampton. Passengers from Cherbourg have the highest survival rate, while those from Southampton have the lowest. Embarkation port may be indirectly linked to passenger class or socioeconomic status. Next, age distribution by survival. This histogram shows age distributions for survivors and non-survivors. Infants and younger passengers have higher survival rates. Orange color survivors outnumber blue fatalities. Many non-survivors were between ages 20 to 40. So age may influence survival, with children possibly prioritized during rescue. Next, fare distribution. This histogram displays the distribution of fares for survivors and non-survivors. Most passengers paid lower fares, 0 to 50. Survivors are more frequent in the higher fare range. Again, fare shows some predictive value, reinforcing its relationship with class and survival. Lastly, fare distribution by survival. This box plot compares the distribution of fares between passengers who survived and those who did not. Survivors generally paid higher fares. Many non-survivors paid low fares, indicating they were likely in lower classes. Fare might be an important factor in predicting survival, potentially reflecting passenger class and cabin location. Here's the quick summary. From the visualizations, we learned the following key insights. Sex matters a lot. Females had a much higher survival rate than males. Gender is a strong predictor. Class is crucial. First-class passengers had the highest survival rate, while third class had the lowest. Fare is informative. Higher fare-paying passengers tended to survive more, likely due to better cabin access and resources. Age has an influence. Young children had relatively better survival rates, possibly due to rescue priority. Embarkation port shows differences. Passengers from Cherbourg had better survival odds compared to other ports. Outliers exist. Fare and age plots show some outliers, but they may carry important information. These patterns suggest that sex, class, fare, age, and embarked are valuable features to include for modeling. Now let's move on to the cleaning step. 5. Cleaning the data. The goal is to fix or remove problems in the dataset, such as missing values, duplicates, or inconsistent formats. Also to prepare a clean, consistent, and machine-readable dataset for training the model. For example, check for missing values with isNull and the sum methods. You'll see missing values in age, cabin, and embarked. Let's drop unnecessary columns, including cabin, such as passenger ID, cabin, ticket, name. These columns are removed. because passenger ID and ticket are irrelevant to the prediction task. Cabin has many missing values. This is too incomplete. Name is hard to quantify without additional processing. Dropping them simplifies the dataset and avoids noise during model training. For meaningful data, let's fill in values. The age column have missing values, so they are filled with the median age. The median is preferred here over the mean because it is less affected by outliers and better represents the central tendency of age in the dataset. About missing embarked values. A few entries had missing embarked values. These were filled using the most common value in the column. This is a safe and simple approach when missing values are few and the mode is clearly dominant. Now you don't have missing values and irrelevant columns. This process matters because messy data causes errors or poor performance during model training. A clean, consistent dataset ensures your model learns patterns correctly. 6. Encoding the data. The goal is to convert categorical features into numerical values so they can be used by machine learning algorithms, which can only process numbers. Machine learning models don't understand text like male or female. We must convert categories into numbers while preserving their meaning. Let's encode sex and embarked. The sex column contains binary categorical values, male and female. We use label encoding for this, which assigns a numerical label to each category. This method is appropriate because there are only 2 categories and no additional columns are needed. Next, encoding the embarked column. The embarked column contains non-ordinal categorical values, S, C, Q, more than 2 categories. As we learned before, we can use one-hot encoding here, which creates separate binary columns for each category. This creates new binary columns, embarked Q and embarked S. We use drop first true to avoid multicollinearity by dropping one category. Embarked C becomes the reference group. This avoids falsely implying an order or ranking between ports. Now the model can interpret the values numerically for both sex and embarked. In some environments, like Jupyter Light, when printing to the notebook directly, the output of pandas get dummies might be formatted as Boolean values, true or false, for display, even though the underlying data is actually numeric, 0 and 1. This is purely a display issue, not a problem with the data. Here's the quick summary of common encoding methods used to convert categorical data into numbers. Label encoding is best for binary categories like male and female, or ordinal ones that have a natural order such as low, medium, and high. It assigns numbers like 0, 1, 2 based on that order. Category codes are a quick way to turn categories into numbers. It works for ordinal or even non-ordinal multi-class categories, but be careful. Models might think there's an order when there isn't. One-hot encoding is ideal for non-ordinal multi-class categories like port names or colors. It creates separate columns with 0 or 1 to indicate the presence of each category without implying any order. Seven, feature selection. In this step, you'll separate the dataset into 2 parts. Features, the input values the model will use to learn patterns. And target, the value you want the model to predict. This step matters because your model learns from features to predict the target. So choosing the right features is critical for accuracy. To select the most relevant features for predicting medical charges, we used a combination of domain knowledge, correlation analysis, and visualization. Based on what we know about the Titanic disaster, we can assume that certain features are likely important, such as women and children were more likely to be rescued. Higher class passengers had better access to lifeboats. Younger passengers may have had higher priority. Fare may reflect socioeconomic status and cabin location. Embarked might indicate regional differences in passenger demographics or cabin assignment. Family connections such as siblings, spouses, and parents' children may influence survival, and so on. To support this, let's check the correlation. This helps find which numerical variables have the strongest linear relationship with the target. This result says sex, class, and fare have a notable correlation with survival. Next, visualization. From the earlier visualization, we know higher survival among females, first-class passengers, and those who paid higher fares. Survival rates varied across embarkation ports. Children had slightly higher survival rates. Based on these insights, let's keep all remaining features after cleaning and encoding. X now contains all the features for prediction, and Y contains the target label, survived. 8. Data split. This step is the same as the regression task. The goal is to separate your dataset into different parts so you can train the model on one set and evaluate it on another set, test or validation data. This prevents overfitting and gives a realistic estimate of performance. Typical training set size is 70 to 80%. Test set is 20 to 30%. This time the test size is 0.2 means 20%. 9. Training. The goal of this step is to train data to teach the model how to learn patterns and predict outcomes. First, import logistic regression, a commonly used classification algorithm from scikit-learn. It's ideal for binary classification problems like this one. Next, create an instance of the logistic regression model. Max iterations 1000 inches sets the maximum number of iterations for the solver to converge. Useful if the default 100 is too low for convergence. Then train the model using the fit method and the training data. The model learns the relationships between the features and the survived label. At this point, the model has been trained and is ready to make predictions on unseen data. 10. Prediction. The goal is to use your trained model to predict whether new or unseen passengers survived or not. Okay, let's predict on the test set. Once you've trained your model using model fit, you can now use it to predict on X test. This will output an array like this. Each value corresponds to the model's guess. 0 means did not survive. 1 is survived. But for now, we don't know if it's correct. Next, let's evaluate the model. 11. Evaluation. The goal is to use evaluation metrics to measure how accurate and reliable your model's predictions are on the test set. Now we are seeing 3 evaluation metrics: accuracy score, classification report, and confusion matrix. Accuracy tells the overall percentage of correct predictions. The classification report provides precision, recall, and F1 score for each class. Precision measures, out of the predicted survivors, how many were correct. Recall measures, out of all actual survivors, how many did the model catch. F1 score tells the balance between precision and recall. In the classification report, support is the number of samples. Macro average is the unweighted average of precision, recall, and F1 score across all classes. It treats all classes equally regardless of how many samples they have. Useful when you want to know how the model performs per class without bias toward larger groups. Weighted average is the average of metrics weighted by the number of support, meaning the number of samples in each class. It accounts for class imbalance by giving more importance to the larger class. It's more reflective of overall performance when the classes are imbalanced. The confusion matrix shows the number of correct and incorrect predictions made by the model, broken down by actual class and predicted class. Here is the quick summary of those metrics. Okay, let's check each result. From the result of accuracy, the model achieved an accuracy of approximately 81%, meaning it correctly predicted whether a passenger survived or not in 81 out of every 100 cases. This is a good result for a baseline model like logistic regression. The classification report provides more detailed insights. For passengers who did not survive Class 0, the model has precision of 0.83, meaning 83% of the time when it predicted did not survive, it was correct. Recall of 0.86, meaning it correctly identified 86% of the actual non-survivors. F1 score of 0.84, indicating strong overall performance for this group. For passengers who did survive Class 1, the model has precision of 0.79, meaning 79% of the predicted survivors were correct. Recall of 0.74, meaning it caught 74% of the actual survivors. F1 score of 0.76, showing reasonable but slightly weaker performance compared to Class 0. Overall, the model performs better at identifying non-survivors than survivors, but the difference is not extreme. Next, the confusion matrix. This is the visualized confusion matrix. 90 passengers were correctly predicted as not surviving. 55 passengers were correctly predicted as surviving. 15 passengers were wrongly predicted as survivors. They actually did not survive. 19 passengers were wrongly predicted as non-survivors. They actually survived. This balanced performance across classes suggests that the model is quite effective, although slightly more conservative in predicting survival. The evaluation shows that logistic regression provides a solid starting point for the Titanic classification task. With an 81% accuracy and well-balanced precision, recall, and F1 scores, the model is able to make reasonable predictions. Future improvements could include trying more complex models like random forest or XGBoost to potentially boost performance further. And that's it for today's lesson on this topic. We explored the Titanic dataset to understand the factors that influence survival. From cleaning and preparing the data to building and evaluating a classification model, you saw how each step contributes to making accurate predictions. Along the way, we also discussed how to interpret results and improve model performance. It's a classic project and a great way to sharpen your skills in data science and machine learning. Okay, thanks for watching today's lesson on coding Fab. I hope you found these tips useful and feel more confident. Remember, practice makes perfect, so try using these tips in your project. If you enjoyed this video, don't forget to give it a thumbs up, share it with your friends, and subscribe for more Fab coding lessons. Until next time, keep practicing and stay Fab.